Hello everyone, and welcome to my first video on this channel. I'm Cy Teaches, I guess, and today I'm going to be showing you how to do source transformations as quick as I can. This will be part of a playlist to help you ace your Intro to Engineering course. It's usually a 200 course. For me, it was Engineering 210, okay, at Case Western Reserve University. Okay, so source transformations, you can, first of all, ignore this left side of my screen. That just helps me draw pretty circuits. Before we actually get into the transformations, there are a few things that you need to know. The first is Ohm's law. You should know Ohm's law, V equals IR. If you don't, there are videos on it. It's pretty simple. And then power is, of course, power is equal to current times voltage. And if you use Ohm's law and plug it in, you can arrive at these other two equations. You should note that power for a voltage source, and there are diagrams on this if you look them up, that in general, you have a voltage source or something, maybe a current source, you want to find the associated power. It's through the positive terminal. It's when the current here is going through that positive terminal, all right? That's when it's equal to the voltage of that source times the current. And if you have a current going this way, the other direction, it's negative I times V. The next things you need to know, just background knowledge, when are things in series versus parallel? It's important to note. Most people don't mess up series. It's pretty simple. If two or more components are on the same wire, you'll note this is the same wire all the way along, connecting to these two different nodes, maybe, that they are in series. There can be infinite components in series. Same with parallel. Parallel, there can be infinite components, of course, but the way parallel components work is that they connect to the same two nodes, essentially like I've drawn, okay? So you could add another thing with like a resistor connecting back up, and those would all be in series, okay? And the voltage drop across all things in parallel is the same, okay? I meant to say this would be parallel, by the way, if I were to add that. Anyway, the reason I note this is because a lot of people mess up parallel. You know something's in parallel if you can draw it with this curvature over here that I've drawn. And I like to do that because it makes sure you don't mess up if there's some resistor here. If there's a resistor, this component would not be in parallel with this component. That's not how it works. They have to connect to the same two nodes with no other components in between. Now, the reason I note this is because for source transformations, we will be using voltage sources in series and resistors in series, and we will also be using current sources in parallel and resistors in parallel. And the reasons for that are these equations as follows. It's very simple. If you have a voltage source or two voltage sources in series, you can add them together if they're on the same wire. If you have the same way, if you have two current sources in parallel, you can add them together, okay? And for resistance, we can actually combine resistors in both ways, okay? So there's a parallel and series way to combine them. The series is very simple, R1 plus R2, and you'll see a lot in school. They'll teach you that R1 parallel R2 is actually R1 to the negative 1 plus R2 to the negative 1 all to the negative 1, okay? And that's true, and that's the best way to do it if you have a bunch of different resistors, but you could also just use the simplified version that only works for two resistors, which is R1 times R2 over R1 plus R2, okay? And that's what I like to use. It makes my life a whole lot easier. The last thing that you need to note is voltage division, okay? These are just all the intro topics. They're very simple, but voltage division is it gives you a little equation to help you when analyzing individual components, which will be your first steps in engineering. So it says if you have some circuit, some one-wire circuit here, okay? So everything has the same current running through it because it's along the same wire, and you have an input voltage and two resistors. So your total voltage drop is across those two resistors. We want to find the voltage across one of those resistors. How do you do that? Well, we see here that I is equal to V in over R, and that's Ohm's law, right? And we can rewrite that as V in over R1 plus R2, because these resistors are in series, and we want the current of the system, right? Because the current's the same across all the components. And then our output voltage we know to be IR2, because Ohm's law again, V equals IR. Okay, but the voltage is different across components, even on the same wire. It's not like current, which is the same throughout a wire at all points, okay? So we then would see Vn over R1 plus R2, which is our equation for current, times R2 is V out. And that's typically written as follows. V out is equal to Vn times this ratio of R2 to R1 plus R2, okay? R2 to the total resistance of the system, all right? And that works for if you were to have another resistor, let's say, like over here, if you were to have like R3, you could just add R3 down in the bottom there, okay? Now, moving on to the transformations, this is the principle of the first topic you'll learn. This right here, everything you see on the screen right here is about simplifying circuits. And what matters here is how do we get from a circuit with a voltage source to a current source so I can combine components, whether that be my resistors, or my sources, my power sources, right? So that will allow us to utilize the above information. Because if we can get two voltage sources in series, we can combine them. If we can get two current sources in parallel, we can combine them. And if we can get two resistors in series or in parallel, we can combine them. All right? So if I have this circuit on the left, I'll underline it with orange. I have this circuit on the left, and I have a voltage source and a resistor, and I want to put my resistor in parallel for some reason, or a current source in parallel with the rest of the circuit connecting to these, terminals, right? Then what I would do is I create this parallel system. So using Ohm's law. So this voltage in series with a resistor becomes a current source in parallel with that same resistor, where this current value is equal to V over R, coming from V equals IR, right? And essentially what that's doing is everything on the left side of these is a component, okay? So the component on the left side here is equal to the component on the left side here. Those two components are equivalent, essentially. And if you don't have to analyze this resistor individually, or this current source individually, or if you started over here, if you don't have to analyze either of these individually, then it helps to simplify, right? It's really important to do so. And if you go backwards, you have the opposite is true, V equals IR, and you go from this parallel circuit on the right here, this parallel current source and resistor, to this series voltage and resistor. And note that the resistor value stays the same. Nothing changes. It's just the value of the source. And I like to say, when going from this left side to right side, I call that series divide current. That's how I remember. So if I have a voltage source and resistor in series, I divide, so that's the voltage divided by the resistor. This is divide, and I get a current source, okay? And now if I have a current source and resistor in parallel, I multiply, it's right here, to get a voltage source, okay? So SDC, PMV, super easy. And that I've noted on the right here that utilizes the above information, which we went through already up here, to simplify circuits. And you should always work outwards, okay? Or inwards, sorry, I apologize. You should always work in words when simplifying circuits. And what that means is if you have a component that you need to analyze, you want to work from the opposite side of the circuit to analyze. Okay, so let's look at an example. Examples seem to be the most helpful way to learn for people. So if we have here an example with a 4 amp current source, I'm not writing down the units because it's just fast for me not to. We have a 4 amp current source, an 8 volt source, a 12 volt source, and 2 resistors of 2 ohms and 4 ohms. And I want to find the power associated with the 12 volt source. I'm going to work from the left side, okay? Because the component I care about that I need isolated is on the right. So I'm going to start over here, okay? Wherever I can. So the first thing I note is that I see current source, resistor in parallel. I'm going to combine them by doing parallel multiply voltage. So, or not combine them. I'm going to reorder, okay? So I have isolated that component. I kind of drew, whatever's on the left side of this over here alone, and then I'll recombine it to the circuit. So multiply 4 by 2 is 8, so I get 4 times 2 and 8 here, and then I keep my resistor value the same, 2, and I've put it now in series instead of in parallel here, right? Now I can just re-add that onto the circuit right here. And the next thing you notice, and I've already drawn, is that we now have 2 voltage sources right here and here in series. And that means we can just add them up, right? Going back to up here. If you have series voltage sources, okay? So we go ahead and do that. And of course, 8 plus 8 is 16. And we keep that 2 ohm resistor in series, and we add that back to the circuit. And the next thing I notice here, because I'm just trying to walk through my thought process because I did very well in this class, and maybe I can provide some insight into kind of how you work these problems, is I notice that these resistors, okay, are the only 2 components I now can analyze, right? Because I have a power source over here, but I can't combine my power source over here with anything. And the reason for that is because this power source on the right-hand side, I need isolated, okay? So there's nothing I can do with this, really. But what I can do is I have resistors, and resistors can always be combined, right? I have resistors, and I don't need to analyze either of them individually. But what I notice is they're not in series, and they're not in parallel, right? Technically, this voltage source and resistor is in series with this resistor, but the 2 resistors are not directly in parallel. So how can I simplify? Well, you can't really get them in series. It's kind of difficult to do, but you can put them in parallel very easily, doing series divide current, right? So I've got my voltage source and resistor in series, these 2 right here, and I can put them in parallel. So 16 divided by 2 gets me 8 as my current source right here, and then I put that 2 ohm resistor now in parallel and add it to the circuit. And that allows me now to directly combine these 2 resistances. And the way I do that is that little trick I taught you guys a moment ago with R1, R2 over R1 plus R2 as the equivalent resistance, and that's 8 over 6. So I now have this following circuit right here with 8 over 6, and that 12 volt source that I need isolated. And I notice, well, this is technically the most simplified version of this circuit, but what I could do to make my life easier is I could make this source a voltage source, because that way I can easily or more easily analyze my 12 volt power source. And the reason that is because if you think, like terms are just easier to analyze than unlike terms. Okay, so if I have 2 things in volts and 1 thing in ohms, that's easier to analyze than 1 thing in volts, 1 thing in ohms, and 1 thing in amperes, right? Also, series circuits tend to be easier for people to look at, depending on what you're analyzing. So here I do parallel multiply voltage, and that's 8 times 8 over 6 gets me 64 over 6 as my voltage source on the left side, and I keep that resistor value the same, and then add that over to my 12 volt source. And we now look, the power associated with that 12 volt source is current times voltage, as we looked at earlier, and we know the voltage to be 12 volts. Now we need to note that the power utilizes voltage coming into that positive terminal. So that's going down like this, right? So I'm treating it as if this voltage is the one that I'm going to keep positive. In essence, I'm subtracting, if I want to combine these like terms as my last step, even though I'm kind of keeping the 12 isolated, I'm going to combine for the purpose of finding current across this resistor. I'm going to subtract this 12 from the 64 over 6, okay? And you'll see why that is in a second, because that keeps current flowing this direction. Even though 12 is greater than whatever 10.66 or whatever it is, so I'll get a negative current going this way. The negative doesn't really matter. Like, sure, current's technically flowing the other direction, but I want the current flowing through the positive side, okay? And if you want to find the current flowing this way because it makes more sense to you, that's fine. Your equation would just then be negative IV, okay? Now, since I know voltage, I need to find current, and current is voltage divided by resistance of the system. So finding the current this direction gets me a voltage 64 over 6 minus 12, minus at 12 volts, over 8 over 6. And I've already done this. Of course, 12 can be written as 12 times 6 over 6, right? And you can multiply the whole system by 6 over 6 and get 12 times 6, 72. 64 minus 72 is negative 8. So negative 8 over 8 is negative 1 amp. As such, you've got 12, negative 1. Multiplying them together gets you negative 12 watts. Now for this next example, I'm going to just go through it faster. I'm not going to go through all the details, just because here I separated every component and recombined, and it's really not that difficult to do. I just wanted to make sure that everyone could grasp the concept fully. So here, this example wants me to find the voltage across the 2 ohm resistor. So that V2 is right here, voltage across the 2 ohm resistor. And what I'm going to do is I'm going to start from this right side, because what I'm analyzing is on the left, okay? So I see immediately that I have nothing that can be combined up front. Even though technically these resistors can, I want to keep my 2 ohm resistor isolated for as long as possible, right? So I can analyze it last, because that's what I care about. That's what the question's asking me to do, okay? So, but what I do see is that if I can turn this into a current source, I can combine it with this current source, because they'll be in parallel. And if I can combine it, and I also notice this resistor and this resistor aren't in parallel, and they aren't in series, but maybe I can turn them into one of the two, right? So immediately I do series divide current. I take my voltage and resistor and turn it into a current source and a resistor. And you'll notice, of course, 24 divided by 6 gets me 4 here. This 24 and 6 turns into that 4. And then I now have some like terms. I've got a resistor and a resistor in parallel, and I've got a current source and current source in parallel. And I know that those can be combined. And you may think, oh, but they're not right next to each other, and didn't you say there couldn't be components in between? I did. That's true. But that's only if the components are along the same wire and don't connect, interfere with the connection between a node. If you notice, like if you were to draw some 3D model, and I gave a little crappy one right here. If I have 4 components, and they all look like resistors here, but it really doesn't matter what they are. If I have 4 components, and I'm connecting to some, system on the left side of this, and I have a resistor 1 right here, and a resistor 2 right here, and like resistor 3 and whatever, resistor 4. They can all be written as like resistor 3 here and 1 here, because I'd just be jumbling the wires around. But they all end up connecting to these same points, right? It really doesn't matter where you are, left, right, or like anywhere in that horizontal region, as long as they connect properly. So what I'm going to do is, because they're all parallel, I can definitely combine the resistors. So 12 and 6 in parallel is 12 times 6 over 12 plus 6, which is 12 times 6 over 18, which is 12 over 3, which is 4. And then my current going downwards, because if you look, there's this current source going downwards of 7, and this current source going upwards of 4. When I add, let's say, 7 plus -4, because they're opposing one another, I get 3. And my current source has a value of 3 amps. So I can redraw both of those in at the same time. I'm not going to do them separate. So I now have this current source of value 3 amps going downwards, and this resistor of value 4. And I know again, I see again, these 2 resistors here are not in series or parallel, but I can make them as such. So what I do is I see parallel multiply voltage, I create a voltage source, and I can now combine these 2 resistors. And 18 plus 4 is 22. So I now have this 22, and I have the most simplified circuit I can. And this shows us, yet again, we can do voltage, or not yet again. Did I do voltage division on this? No, I did not. I'm getting confused. We can do voltage division, okay? We know that the output voltage from here to here, V2, our output voltage, is equal to the input voltage times the ratio of the resistor we care about over the total resistance of the system. So that would be 12 times 2 over 24, which is equal to 1 volt. And that is the associated voltage with the 2 ohm resistor. I'll post a video hopefully tomorrow regarding KVL and KCL. They're pretty simple topics, but you'll need them in the first unit of your intro to engineering course, whatever it may be.